a fifth of 6 live classes that we're doing for chemistry. So what we're doing today is we're looking at some H-NMR. Like, I'm pretty sure that's everybody's favorite, right? Correct me if I'm wrong. So I know that, you know, whenever I speak to students about like what do you want to revise, what sort of questions you want to do, like week on week when we do our weekly web classes, guaranteed somebody somewhere is going to say H-NMR. So we had to throw this in there. Of course we did. So who have we got in the Zoom chat? We got Megan, we got Imran, Ellen, Forrest, Michelle, Esha, Sarah. Hello, hello, hello. Welcome, welcome, welcome. So when you're in the Zoom chat, just make sure, if you haven't already, you click that blue button at the bottom that says all panelists and attendees, and that way your question, your comment can get seen by everybody and not just me, and then everybody knows what we're talking about. In the YouTube, Amrapal, hello, welcome back. Welcome back. So we're going to do some H-NMR. Hopefully yesterday, it seemed like a big win yesterday. Lots of people found that session really, really useful on buffer questions. There are 3 types of buffer questions. It's nice when we can kind of compartmentalize and, you know, visualize what's going on with the calculations and stuff. We've got Evan, we've got Alice. Hello, welcome in the YouTube. So as I've mentioned, like all last week, all this week, hey ML, if you're in the YouTube and you want to get involved with the Zoom chat during the live and ask questions during the live, then you can just click the link at the bottom in the description and you can join the chemistry free trial. But you don't have to just do the chemistry free trial. You can do you know, the biology and maths ones as well. If you want to join those, that's absolutely fine. But you get 7 days and you can join us. Okay. Stephen, yesterday didn't have any buffers in your exam, so just did some course lessons instead. Perfect. Okay, no point kind of flogging a dead horse there, is there, to use an old phrase. So, you know, you don't want to have to revise things that you don't need to. We're all about that here at TT, aren't we? So, you know, you're not going to get any comments from me about not coming yesterday because it wasn't relevant. So, so yeah, today's all about H-NMR. Now, what I'm going to assume is that everybody who's doing this, obviously it's a year 13 topic, not a year 12 topic, but if you're a year 12 and you're at a loose end and you feel like learning a bit about H-NMR, then you're in the right place, because we're going to talk about the fundamentals. Because what I would say is there are no, you're probably going to hate me for saying this, but I don't think there are any difficult H-NMR questions, all right? Because when it comes to H-NMR questions, you know, a lot of the time they're like, oh, try and find the structure of this molecule. But it's usually like a good number of marks, 4, 5, 6, 7 marks. But you don't get those marks for finding that end product. You get the marks for the process going through it, and the process going through it, the insights that you have to make based on the information they give you, that's where all the marks are from. So what this session is going to be focusing on are, of course, those insights. How do we actually, you know, look at the 4 major things, or the 4 different things that H-NMR can tell us about a molecule? We're going to be using a PDF to do that. Now, in the description in YouTube and underneath the join live button in the course, then that's where you'll find the PDF for today, called the H-NMR Masterclass. So what you want to make sure is that when we start, you've got access to that PDF, whether it's on the screen next to the video or you've printed it out. Okay, if you've printed it out super duper quick, that's absolutely fine. And I'm just going to give you just another couple of minutes to go ahead and do that before we start. So, what can I say about this year? I mean, all I'm seeing on social media, just while you guys are getting self-set up with the PDF, is that they've cancelled the exams and then put it in teachers' hands. But of course, the first thing teachers are going to do is be assessing you, and they're going to assess you as soon as possible. So if anything, they've brought it forward. So I really feel for you guys right now. This is not a normal year. Year 12s, we are keeping everything crossed for a normal year next year, okay? And I think, you know, this whole process, and you know what, wider than education, you'd like to think that there are some things in our society and life and the way things are done that actually we can reflect on and we can improve on. And I'm hoping there's going to be some things in education that's going to happen there. So I'm getting a bit deep today, getting a bit deep. So what's happening with assessments? Well, I mean, the exam boards have written some assessments that are going to give to teachers. They said they're going to make them publicly available after Easter. Now, of course, we're officially after Easter right now, but maybe that's the end of this week or the beginning of next week. So I know some of you are still off school and college. You haven't gone back yet. But when they do, when they are released publicly, that means we can kind of go through those with you and we can take a look at them together. And we may do that here at TT for our members. So we can analyze those papers, take a look at them, because if they're freely available to everybody, then there's no reason why we can't do that. Okay. So Amritpal, are they like papers or topic assessments from the exam board? So I would say they're split into two or three depending on the subject. From what I've seen so far, there's kind of like a physical chemistry, an inorganic chemistry, and an organic chemistry one that they've done. So when are they getting released in the Zoom chat? Well, as I say, they're releasing them after Easter. Michelle saying 19th of April. I'm not sure where that information has come from, but a few people saying 19th of April. Yeah, it sounds about right. So it does seem they are releasing them publicly. Whether that's a good thing or not, we don't know. But of course, teachers don't have to use them. Teachers can give you their own assessments. But of course, you know, when teachers are writing their own assessments, they have to make sure they're balanced. They have to make sure they're of a good, you know, a decent difficulty, not too easy, not too hard. It's a really difficult skill. So yeah, I think if they are releasing them publicly, then it'll be worth, you know, I think teachers will use them, but whether they'll use them really early on or later on, I don't know. But of course, your marks have to be in by the 18th of June to the exam board. So my guess is that no teacher really is going to be assessing after the first week in June. That'll be like the last chance saloon for you guys to be assessed. And then of course, year 13s, what that means for you is you're free and easy. You're free to finish and do what you want for the summer and enjoy your summer, which will be, you know what, it'll be amazing. It'll be like a massive party, because hopefully, you know, come the end of June, the 21st of June, you know, according to Boris's roadmap, then we're all free to kind of do what we want, and restrictions are largely eased, and we're back to some sort of normality, which would be amazing. But, you know, we'll just have to wait and see. Right now, I'm in Wales. I'm a little bit jealous. I don't want to talk about easing of restrictions because everybody in England can go to the beer gardens, whereas we're not allowed yet. We've got to wait for another week or so yet, but there we go. Subnam, yeah. So to avoid people leaking them, they're just giving them to everyone. I mean, yeah, I can kind of see the logic in that, but then that doesn't really make sense to give everybody access to the papers. I don't know. There we go. Who knows whether it's the right or wrong decision? I don't know. But there we go. Excuse me. Surely there's not going to be that many questions. They're not very big from what I've seen. They're not very big. So they are mini assessments, mini exams. Okay. And those exams, I should say, those things they've put together are largely made up of already released questions. There may be some unreleased questions in there that haven't been released publicly already. So it's a mixture of the two from what I've seen. It's a mixture of the two. Oh, thank you very much. I am a doggy dad, even though he's not here right now. No Dexter today. Dexter's having his hair cut. So it's all right taking him out for a big walk afterwards. Get him nice and muddy after he's had a bath and a haircut. Right, we should crack on. We spent 10 minutes. So has everybody got their PDF? Like I said, it's in the description of the YouTube and it's underneath the Join Live Class button on the Live Class page where you guys just joined. Make sure you've got hold of that. I mean, you can make notes on a separate bit of paper in a notebook if you want, but ideally, you know, you should be writing notes on this PDF. I put it up there first thing this morning. So let's get going. Let's get going on H-NMR, okay? So let's do a quick intro. Share your screen. Come on, iPad. There she is. Right. Okay. Oops. Need my pen. Okay. So H-NMR. What does it stand for? Do we even care? Well, we should do really a little bit. Hydrogen 1 NMR. Okay. So what is this? Nuclear magnetic resonance spectroscopy. Essentially, the protons in a hydrogen atom, of course, we've got one proton and one electron flying around. It has a spin. And by applying a magnetic field, we can alter that spin, you know, really loosely kind of explaining that there. We can alter that spin, and then how that spin alters gives us an indication of what environment a hydrogen lives in on the molecule. Okay. So if we've got an organic molecule, of course, it's littered with hydrogens. So just propane here. Okay. We've got 6 hydrogens on there. Now, what it can tell us is where that hydrogen is relative to other atoms in the molecule. So when I talk about environments, I'm talking about, a unique place where a hydrogen atom lives on a molecule. So let's just take something simple like methane, for example. All of these hydrogens, okay, live relatively in the same position as each other. Okay, they're all bonded to that central carbon. That central carbon's bonded to 3 other hydrogens. They are absolutely exactly the same as each other in terms of environments. Now, when we come to a different molecule like propane, for example, we haven't just got one environment, but we've got 2. So these 3 hydrogens all bonded to the same carbon. I think that's a bottom line there. If you're looking for an environment, if all the hydrogens are bonded to the same carbon, they are all in the same environment. So we can agree that these on the left-hand side are all the same environment. What about these ones on the right-hand side? Is that a different environment, or are they the same environment as the ones on the left? Different or the same? The same, absolutely, because this is a CH3 on the end of a chain, and it's literally a mirror image, isn't it, of the left-hand side. So all of those in yellow there on the propane molecule are in the same environment. So I know they exist separately. They are 2 separate things, but according to their relative position in the molecule, they're all on a CH3 or in a CH3 bonded to a CH2. So both exactly the same. So what we can say is that lastly, these 2 hydrogens in the middle, they're not in a CH3, they're in a CH2. They exist uniquely on their own in the middle of the molecule. So this is what we're doing. By looking at the spectrum that we get from H-NMR, we can tell how many different environments there are, how many hydrogens there are in each environment, what hydrogens they're next to, and what type of environment it is. So there's 4 major things that we can learn from the spectrum of a H-NMR. Now, what I'll say before we start is what we're doing is creating spectra today. We're analyzing molecules and creating spectra. Now, I know in an assessment, in a live class scenario, in a live exam scenario, 9 times out of 10, probably more than that, you're going to get a spectrum, which then you need to use in order to construct a molecule and see if you can deduce the structure of the molecule. So what we're doing is reverse engineering it, because what I found over the years when teaching this is that doing it the other way, looking at a molecule and creating the spectrum as you go, that helps your understanding a bit more as to what that spectrum is showing you, okay? Because every time you look at a new spectrum, you kind of like, I don't know, you need more information than just the H-NMR to draw a molecule. So it makes it really, really difficult because you know as well as I do, you've seen in papers, that you get some information, you get the H-NMR spectra, but you'll have other information as well. So from your experience, guys, what sort of information do you also get in H-NMR questions to help you get the answer? CNMR, molecular formula, absolutely. IR spectrum, yeah, good. Maybe even some chemical tests, okay? So maybe it reacts with failings or something like that as well. So chemical tests, IR, mass spectrum, maybe percentage abundances of the elements in there, so you can work out the empirical formula and then you can work out a molecular formula. So there's all sorts of other things going on. So that makes it really difficult to learn in that way, because if you just get the H-NMR spectrum, you pretty much haven't got a chance of being able to deduce the structure of the molecule, okay? So by doing it the other way, you're focusing on the H-NMR. You've not got all that other stuff going on. You can really focus down on what's important, and that's understanding A, how this works, and B, how to analyze the spectrum as well by reverse engineering the process. So that's what we're doing today, ladies and gentlemen, okay? So first and foremost, I would say that if you haven't already, dig out your data sheet for your exam board. Okay, we're working with our own individual data sheets today, so you do need these. Okay, so in the Excel data sheet, any of those, this is what yours looks like, ladies and gentlemen. So you got your chemical shift at the bottom. Don't worry, we're going to go through all of this, and you can see the different types of hydrogen environment. All the hydrogens are bold in there. You can see what type of environment we're looking at. AQA looks a bit like this. It's more of a list that we've got in the middle here. So you can again see they're highlighting these hydrogens and they're saying, right, well, if it's got a chemical shift of this, then it's a hydrogen in this environment. So it's just a lookup table. That's all these are. And then lastly, we've got our OCR, which is the other example we do here at TT. And that looks different again, you lucky people. So it's the one down the bottom here, okay, the H-NMR. And that is, again, highlighting the hydrogens on these different groups. So OH and NH could be anywhere along this stretch of chemical shift here, and so on and so forth. So I don't know. I don't think I've got a favorite, but you know what? It doesn't matter, because you have to use the one that's given to you. Okay, you have to use the one that's given to you. So we'll be using this a little later on. We're going to start with something different first of all. So H-NMR Masterclass. So as I mentioned, there are 4 things that a H-NMR spectrum can tell you about a molecule. It's really, really important. You're really clued in on those 4 things. And just like we did yesterday, by being methodical with the analyzing of these, one thing at a time, then that's what's going to get you the marks in H-NMR questions, okay? So molecular feature and H-NMR spectrum feature. So what I'm going to say here is molecular feature is the number of H1 environments in the molecule. Okay, so when we look at a molecule, we need to be able to say, right, it's got X number of environments. Okay, we need to be able to spot those environments. That's a really, really important skill. Now, how is that reflected in the H-NMR spectrum? So the readout that we get from the spectrometer, what do we see if the number of hydrogen environments equals what when it comes to the spectrum? Sarah, Emily, Fatea, number of peaks, absolutely. Okay, Shania as well. So this is equals the number of peaks in the spectrum. Okay, so the number of peaks you get in the spectrum, that equals the number of hydrogen environments you have. Okay, so what I've done with this worksheet is we're going to work through these individual things one at a time. Okay, so the first thing we're going to do is we're going to practice this skill, spotting hydrogen environments and therefore number of peaks in the spectrum. So over the page to the first one. On these pages, okay, I've done a few things. I've given you a molecule in the top left-hand corner. I've given you a little space to write any notes that you want, okay? So if you think, oh, that's a good thing to remember, just pop it in there. Then we're going to fill out this table. And at the bottom, the very last thing we're going to do before we finish today, draw the spectra for these different molecules, okay, to see what they're going to look like. So we're all going to do that together. But like I said, we're going to go through each of these 4 times, okay? First time through, we're going to write out the number of environments, okay? And we're going to spot what environments that we've got. So we're looking at ethanol. Nice and easy one to start with. So how many environments can we see? Pop it in the chat there, guys. 3 hydrogen environments. I think you'd be absolutely correct there, okay? So what are our environments, okay? So our first environment I'm going to write in here is a CH3. Okay, so that's an environment on its own. On the left-hand side there, we've got a CH3. We've also got a CH2 environment, okay? But what's special about this CH2 environment? We need to just think about what's next to it as well, rather than spotting the environments. What's slightly different about this? What's quirky about this? We're not talking about splitting patterns yet. Sam's asking about splitting pattern. But just looking at what it's bonded to, Fatima, absolutely. It's bonded to an oxygen. So I'm going to write an OCH2 there because you know what? That's an important feature. You know, anything that's not carbon or hydrogen, I think that's an important feature. It's bonded to something different, whether it's a nitrogen, whether it's a double bond O, whether it's an oxygen, whether it's a chlorine or something like that. So I would put that down as a CH2 next to an O. But it's also, if I can move this, in fact, ooh, it didn't move me O. It's also a CH2 next to a CH3. Oops. Okay, so both of these are the same. It's got an O on one side and a CH3 on the other, because that, when we look later on at our data sheet, that could be the difference, okay? Is it a CH2 next to an O? Is it a CH2 next to a CH3? Well, it's kind of both. So it could feature in either of those parts, okay? So let's try and get an overview of exactly where this CH2 is. It's really, really important. And actually thinking about that, we should really put an R, or you could write CH2, CH3, you know, and always underline the hydrogen environment that you're looking at, because that will help you when you're looking at the data sheet. Okay, you could put the hydrogen in bold like they do on the data sheet or something like that. But then we've got one more environment, and that is an OH. Okay, so that is the OH. That is our third and final environment here. Okay, so does everyone understand what we're doing here? We're looking for the number of environments. We've got 1, 2, and 3. What I'm doing in that environment column is writing down what it is and what it's bonded to, what it's next to. Okay, so it's a really important thing, that, and it's a lot of things. It's something that a lot of students don't do when they're analyzing this. They just go, let's go 3 environments, without really looking at where that environment is relative to the rest of the molecule. Okay, so what I'm going to do is I'm going to give you, we've got 5 more to do. Okay, we've got propane. We've got an amino acid that I've given you. I think that's, is it glycine? No, it's not glycine. Glycine's got 2 hydrogens on it. That's got a CH3 on it. I'm not a biologist. So we got 3-chloropentane, we've got 2-chloropentane, and we've got methyl benzene. So what I'd like you to do, please, is do the same as we've done for ethanol here, and just obviously the number that you fill in, that's the number of environments, but please just make sure that you write down where that is. Okay, where's that hydrogen environment relative to other things, as best you can. There's no rules here, okay, but it's just making sure you understand and can spot what else is around it. Okay, so we're not just listing a number of environments here, we're actually saying where they are. So I think there's 5 here, so I'm going to give you guys, let's say 8 minutes, and see how we go. Okay, so let me bring up Mariah here. Where are we? Okay. Oop. There we go. 8 minutes. Starting now, guys. Off you go. And I'm going to do the same thing. I'm going to go through it myself and do it, okay? And we can look at our answers later. Okay, guys, time check, 3.5 minutes. Okay, in the Zoom chat, if you want to tell me when you're done, that's absolutely fine. Just hit, type done or something like that. It gives me an idea of where we're up to. Thanks, Shania. Okay, 2 minutes left, guys. I just want to give you enough time to do this. I don't want to rush you. Okay. So quite a few people in the Zoom chat done now, which is awesome. Asher as well. Okay, last minute, guys. Just be patient while other people finish up. That's all good. Maybe I gave you a bit too long for this. So, of course, this is going to stay in the course. All these videos are going to stay in the course if you're working on the recording. Hopefully, you're going to get these done in time. Same for YouTube. These are going to stay on YouTube for a bit as well to help people. Okay, last 10 seconds. I won't do teacher minutes and seconds. I will do actual minutes and seconds. We've all been there and the teacher's like, right, I'm going to give you 10 minutes to do this. And then 20 minutes later. There we go. Right. Okay. So we did the first one, okay, together. Well, I showed you what we're doing. So for propane, there should only be 2 environments, ladies and gentlemen. What I've done here is I've said the CH3, so this one or this one, because they're both equivalent to each other. That's a really important word, equivalent. Okay, when you got 2 environments, or the same environment, but in 2 places, are known as equivalents. I've put that as RCH3 because sometimes you see it in the data sheet like that. But I've been specific here and said, well, the R group that's attached to the CH3 is a CH2. So you can see, again, I'm underlining the CH3 there. And we've got that CH2 between the 2 R groups. In other words, the 2 CH3s. So we've only got 2 environments there. Over the page, we've got 4 environments. We've got the OH. And notice I put acid underneath it as well, because that's helpful, just in case you have got a question whereby you got some IR data. So that's really, really important. This one here, number 2, and I'm focusing on this one here, okay, it's a H bonded to a C next to an N. So I'm looking at this kind of grouping here, but I'm also looking at this grouping here. It's a H bonded to a C that's in a carboxylic acid as well. So I've just done both there just so I can say to myself, I know exactly where that hydrogen is. And it looks confusing when you see them separately like this, but you know, it's in two positions. In fact, what you could do is just draw the entire position of that H like so. So you could just put, there's the H, there's the carboxylic acid, there's the N. I mean, we've got an R group up there, but we end up drawing the whole molecule, don't we? Okay, so that's what I've done there. In fact, I'll bring it back to what I had before. We've got a CH3 on here, this one here, which is bonded to a CH. I don't think the N is going to have any impact on that there, but then we've got our NH as well. We got two of those bad boys in an amine group. So 4 different environments. Whoops. Next one, we've got 3-chloropentane. So we've got an RCH3, okay? We've got a CH2, which is next to a Cl, like so, on both sides, okay, like that. And we've got a H that's next to, that's also bonded to a carbon, that's also bonded to a chlorine. So we've got that one in the middle. So 3 environments there. Now, a very similar molecule, but you can just see how such a big difference it makes. Only 3 environments here, but where we've got this symmetrical molecule, where you have symmetry, and I put this in your notes, equals fewer environments. So where you see a symmetrical molecule, you're going to have fewer environments because, of course, you know, we've got like, well, I suppose 1, 2, 3, 4, 5, 6 different places where we can find, 5 different places where we can find a hydrogen, but 2 of them are equivalent, aren't they? Or 4 of them equivalent. So symmetry, fewer environments, just a nice little kind of thing to hang your hat on there. Of course, when we shift that chlorine just 1 to the left, so 2-chloropentane, we end up with 5 different environments here, okay? So the CH3 on the end here next to that CCl. We've got the H that's bonded to the same carbon as the Cl. We've got a CH2 next to that CCl, so it's all relative to where that CCl is. We've got a CH2 that's just basically between 2 R groups. So we've got an R and a CH3 there. And then, oops, I won't undo that. And then lastly, we've got that other CH3 on the end, which is different to the other CH3, okay? So this CH3 and this CH3 are different. The reason being they're bonded to different things, okay? This is bonded to a CH2. This CH3 is bonded to a CHCl. So they don't exist in exactly the same place, okay? We haven't got that symmetrical thing going on like we did in the last molecule. So 5 different environments here. And then lastly, one that gives some people some trouble is benzene, which is why I put one in here. We've got an alkyl CH3 up here that's bonded to the benzene ring, really important, which is why I've just basically drawn the whole molecule again there. We've got these H's here, which are basically these bad boys. Remember, it's benzene. There's only 1 hydrogen on each carbon in the ring. So they're next to the alkyl group. You've got the other CHs down here, which are not next to the methyl group. And then lastly, you've got this hydrogen at the bottom here on its own. And that's the last one, the last environment, okay? So we've got 4 environments here for methyl benzene. Oh, see you, Megan. CFRDE. I don't know what CFRDE means. So yeah, 4 environments here. And again, we've got this symmetrical thing going on, okay? So if you draw a line down the middle, these 2 are equivalent, these 2 are equivalent, and this one's on its own, okay? Emily, good. I'm glad this has made an impact already for you, okay? Didn't understand how to draw it out now, but now you do, okay? So you get an idea. So let's do the next thing. So we can identify environments, and it's important not to just go, oh, well, there's the environments. Just stop and think just for a couple of seconds about where that hydrogen is relative to other things, because it's going to help you when you start looking at your data sheet. Now, back to the first page. Number of hydrogen environments equals the number of peaks in the spectrum. So the number of hydrogens in each environment, how is that reflected in our spectrum, guys? So we've got a number of environments now, but there's maybe 2 hydrogens in this one, 3 in this one, so on and so forth. Boom. So that equals relative peak height or relative, what do we say? Integration value, or it could be integration value. Now, if you haven't heard the term integration value and your OCR at Excel or any other exam board apart from AQA, that's okay. If you're AQA and you haven't heard the term integration value, then you need to know it, because that's what they refer to it as for AQA, the integration value, and you may see that, okay? So they may put a little number next to the peak, or you may just look at these peaks relatively speaking, okay? So literally all we're doing here is looking at the relative peak height or integration value for each of these different environments, okay? So literally just putting a number in the box here, okay? And saying how many hydrogens are going to be in each peak, okay? So, or relative peak height. So I'm going to get you to do that for all 6. I'm going to give you just 2 minutes. That's all I'm going to give you for this one. 2 minutes, guys. And your time starts now. 2 minutes. Shouldn't even take you that 2 minutes. You've had just over half your time, 50 seconds left. Oh. Imran, there was one NMR question I got recently, time's up, where my teacher said no student had ever got the right answer in the history of teaching, or in her history of teaching. Well, that's a little bit mean, isn't it? Maybe it was an ether with a secondary alcohol. See, ethers, that's why nobody's getting it right, because you know what? The ether's not in anybody's spec, right? AQA, OCR, and XL, ethers are not in there, okay? So you'd be absolutely forgiven for not getting that right if you've not been taught what an ether is. So yeah, no wonder. But you wrote down ether, but you just got primary alcohol. Oh, so far, but yet so close, or so close yet so far. I don't know. Anyway, so what I've got here, just check your answers, guys. We got 3 to 2 to 1 for our ethanol. Over here, we've got 6 to 2. Now, at this point, I want to highlight the fact that this is relative. So what could your integration values be, or your peak heights, actually? Yeah, it could be 3 to 1. Okay, absolutely. It could be 3 to 1. Okay, because we're talking relative values here. And in AQA, if they give you, like, you know, they can be in decimal places, some of these. You just have to work out, you know, what the simplest, you know, integer rate relationship is. Okay, and that will 99% of the time, the numbers that you see, if they're whole numbers, they're going to be the actual numbers of hydrogens, but you need to just be aware that it could be relative. So it could be a 3 to 1 peak height ratio, or indeed it could be 6 to 2. You just have to know that. Of course, knowing the molecular formula, knowing how many hydrogens you've got in the molecule is the only way you're able to figure that out. Okay. So That's this one, 6-2 or 3-1, either or. This one's 1-1-3-2. We got one for our OH acid, one for our hydrogen in the middle of the molecule, 3 for our CH3, and 2 for our NH2. 3-chloropentane, we got 6, 4, and 1. This is 6 because there's 6 hydrogens all in the same environment there, 2 lots of CH3. Little word to the wise, peak height of 6 equals usually 2 equivalent, CH3s. Okay, so when you see that, alarm bells go off in my head saying, right, if there's a peak height of 6, then there's probably 2 equivalent CH3s here, as there are in this molecule. Okay, so it's no coincidence. So you just, these little patterns, you know, that you write down, you make a note of, they do tend to help, like the symmetry thing as well. So 6, 4, 1. And then this one, which we can't simplify, actually, for the simple reason you can't simplify that any further. Okay, you might, AQA people, see it 3 to 0.5, but of course you can't get 0.5 of a hydrogen, can you? So logic would dictate I need to double that and make sure I've got a whole hydrogen there. And then last one, 3, 1, 2, 2, 3 in the order that I wrote it. Okay, so again, can't simplify that. And then lastly, we've got 3, 2, 2, and 1. All right, again, not able to simplify that one. So we've got now the number of environments, the number of hydrogens we have in each environment. Again, last thing I would say is that with these relative peak heights or integration values, 99% of the time, they are the actual number of hydrogens in the molecule. But I would find the total. If you get that from the spectrum you're reading, look at the total number of hydrogens. It would normally, I would say, a lot of the time, equal the number of hydrogens in your molecule. So you know you're set then, you know those two things match up. The number of hydrogens you actually have in the molecular formula, and of course, the sum of your relative peak heights. That's just a nice little double check there, a little kind of common sense check, I would call it, just to make sure that you're on track with your analysis, okay? Now, fun times, everyone. We're going to be looking at splitting patterns. Everyone loves splitting patterns. So I would say that is the number of neighboring hydrogens I'm going to write that differently. So it's the number of hydrogens on neighboring environments. Okay, number of hydrogens on neighboring environments. Okay, adjacent, yeah, adjacent is a good way of saying it as well. They do love saying adjacent in mark schemes, but I'm going to say neighboring. Okay, so the number of hydrogens on neighboring environments, what does that equal in terms of our spectrum feature, guys? You don't just say splitting pattern, be specific. Good. Sam's saying n+1 rule. So the split equals 1 more than the number of hydrogens on neighboring carbons. Now, I've been specific in terms of carbons here, okay, because it has to be a carbon, all right? So if you've got a neighboring nitrogen with some hydrogens on, no splitting, okay? So there's a couple of rules here we'll write down. In fact, where am I going to put this? Maybe I didn't make this box big enough, okay? So I would say that rule number 1 has to be carbon, okay? NO or anything like that, no splitting. It doesn't cause any splitting if you've got an OH next to it or an NH next to it. There's no splitting caused, okay? Shania, I'm going to come across, we're going to talk about that right now. So Shania's just asked, for those of you in YouTube, if there are any hydrogens on both sides of the carbon, do you add them all? Well, it depends, okay? So the second thing here is that neighboring hydrogens are cumulative unless, I'm going into the next box here, I'm sorry, guys, they are equivalent to each other, okay? So if you've got like a CH2 on one side and a CH3 on the other, that's 5 neighboring, so that's 5 hydrogens on neighboring carbons, okay? So you'd get a sextet, you get a multiplet. Yeah, absolutely. But if you had a CH3 on one side and the equivalent CH3 on the other, which we're going to see in a second, they are not cumulative. You'd only get a splitting pattern of a quartet rather than a septet, okay? So 6 neighboring hydrogens. If they're both equivalent to each other, if both of these CH3s that we're going to see in a second are equivalent to each other, yeah, if they're symmetrical. No, not if they're symmetrical, you don't count both. You don't count both. So one environment can only cause one set of splitting, okay? So if both of the neighboring carbons with hydrogens on are equivalent to each other, then they can only impact the splitting once, okay? But if you've got 2 different hydrogen environments either side, then they're going to be cumulative and they're going to do that, okay? Wow, okay. So yeah, that's a really important thing. So a few of you in the Zoom chat didn't know that, okay? So it's a really, really important aspect to this, and it's going to, hopefully, it's going to help you with a lot of questions moving forward. So let's go through the motion, shall we, guys? So we tend to use terms for splitting patterns: singlet, doublet, triplet, quartet, and then anything after that is a multiplet, okay? We can say, what's 5? I've forgotten what 5 is. So different environments either side, Sam, are cumulative, yes, okay? But if they're the same environment either side, then they're not cumulative, okay? So pentet, is it a pentet? Yeah, hextet. No, there's a sextet and heptet. Anyway, quintet, that's the one. Thank you, dear. Quintet, I should have known that, okay? But anyway, multiplet, shall we say, okay? So let's have a look at these then. So we've got ethanol. And Ellen. Oh, sorry, Ellen as well. I didn't see that one. Thank you very much. So we've got our CH3 on the end here. So it's only got one neighbor, which is this CH2. So the splitting pattern for this, okay, don't forget, this is where it gets a bit tricky because we're focusing on the environment, but we're now looking at the neighbors as well. So for this environment, for the CH3 environment, it's going to be what for this one here? What's the splitting pattern going to be? It's going to be a triplet. Good. Okay, this is going to be a triplet because there's only one neighbor that's carbon with 2 hydrogens on, so it's going to cause a triplet. So we tend to draw a triplet like that. The central one is always taller than the other 2. It's just the way they're drawn. Okay, so it's going to be a triplet. The CH2, what's that going to be? That's going to be a quartet. Fantastic. This is going to be a quartet. Now, the reason, okay, is that this CH3 is causing that environment to split, that CH2 environment to split. But this one, even though it's bonded to an atom that's next to it, doesn't cause splitting. So the OHs and NHs do not cause splitting. And you're already saying it in the chat that OH itself, okay, is indeed a singlet. NHs and OHs are always a singlet peak because, there's the O and the N, think of them as blockers. Okay, so think of the message can't get through. The message of splitting can only get through a carbon. It can't get through an oxygen. It can't get through a nitrogen. They're the only other 2 things that you're going to come across in terms of these molecules. Okay, of course, you can have halogens in there as well, but that's one-way traffic. It can only bond to one thing, can't they? So it's always going to be at the end of something, a halogen anyway. Okay, so there's not going to be another hydrogen bonded to that. So it's O or N, no splitting. Okay, either way. Okay, so the hydrogen or the hydrogen on a alcohol or an amine doesn't cause splitting on anything else, the other side of the nitrogen or oxygen. But the things on the other side of the nitrogen oxygen don't cause splitting on the OH or the NH either. Okay, so if you see an N or an O, no traffic, message can't get through for splitting. Okay, think of it that way. So, you know what? I'm going to get you guys to do the other 5, and I'm going to give you just 5 minutes to do that, if that's okay with you. Well, I say that. It's tough. You're having 5 minutes. Go. and I shall do the same thing. Oh, sorry. Forgot to pause. I was in the zone then, guys. Okay, 2 minutes left, guys. Okay, just 1 minute left. And there we have it. So For the second time, I'm going to show you my answers. Okay. So in this first one, we did together triplet, quartet, singlet. So in propane, we've got a triplet and a quartet. Okay, a triplet and a quartet. Sam, I'm pretty sure Ronnie's doing something on Thursday. Pretty sure she's doing a regular live class on Thursday. So we've got a triplet and a quartet here. This is a triplet, okay? This CH3, okay, or this CH3. The reason being, it's only these hydrogens that are having that effect on the splitting pattern there, okay? Now, so basically you just focus on one of them. So where you've got these equivalent environments, just look at one and, because they're equivalent, they'll have the same neighbors, won't they? All right. So just look at one of those equivalent environments and then you'll get your answer. Lastly, this middle one is what I was talking about before. So we've got this central environment here. In fact, I'll highlight it like so. The purple is what we're focusing on, okay? And the red is going to be the neighbors. Now, because these two neighbors here, all right, are equivalent to each other, they are the same environment, they can only have an impact on the splitting pattern once. They do not double up, which is why this is a quartet. So we take one of these, okay, and that influences the splitting pattern of the CH2 in the middle. So N+1 rule, 3 of those, so that means it's going to be a quartet. Okay, so it's really, really important that you know that, okay, because otherwise you're going to end up tying yourself in knots thinking, well, that's meant to be an octet. It's meant to be a massive multiplet. Why is it not there? Well, because, you've got these equivalent environments, so they don't do that. That's a really important aspect, okay? So if you didn't know that before, you know it now and everyone's a winner, right? So next one, lots to do here. We've got a singlet for our OH, standard. We've also got a singlet for our NH at the bottom, standard. The one in the middle, this hydrogen here, okay, focus on this one. This is a quartet. Now, the quartet's not coming from here, and it's not coming from here. It's coming from this CH3, okay, because that is the neighbor of that, okay? So that CH3 there is causing the quartet. Of course, because this carbon has no hydrogens directly bonded to it, N cancels the signal. Yeah, no signal getting through there. And then lastly, this CH3 up here, that is for the same reasons, no information, no splitting pattern coming from either side there, but you are getting a splitting pattern from the single hydrogen, which causes it to be a doublet. Okay, really, really important, that one. All right, doublet. And then over the page, we get to the bigger molecule. We've got 3-chloropentane. So the CH3, okay, this is these two equivalent environments. Again, I put quartet down for that. It's not quartet at all, is it? It's triplet. Do apologize. As soon as I looked at it then, I'm like, that's wrong. So this is a triplet, okay, for the same reasons as before. These two are equivalent to each other. They're only going to cause one lot of splitting, okay? So that's why it's a triplet. Oops. The CH2s, which I'll do, in fact, let me just tidy this up a little bit. It's hard to keep drawing over and over things. These CH2s, for the same reason, because you only count the CH3 once, okay, because they're equivalent. But we've also got this cheeky little one here, okay, which is why it's a multiplet of 5. Okay, it's a quintet, which I've just relearned. So that'll be a multiplet of 5, that CH2 group. And then the CH all on its own in the middle. If I just get rid of these, this H all on its own in the middle, again, for the same reasons. It's got 2 CH2 neighbors, but it's only one of them is going to cause a splitting pattern. So that's why we end up with that triplet, okay? Fifth one, lots more going on here, lots and lots and lots. So the CH3 next to the Cl. So this one here, okay, has only got this one hydrogen that's causing the splitting pattern as a neighbor. So that's going to be causing a doublet. Next up, we've got the single hydrogen. Now this has 2 inputs. It's got a CH3 and it's got a CH2 as neighbors, which is why it's a sextet. It's a multiplet with 6 peaks in, okay, because we've got 2 non-equivalent, okay. The last one for the one before, Sam, was triplet. I do apologize. Sam's asking that in the Zoom. So it's that CH there, the second one along. That's going to be a multiplet because you've got two different environments next to it, the CH2 and a CH3. Next up is this CH2 group here. Its neighbors are this CH and this CH2. They're non-equivalent, which is why this is a quartet. Okay, looking either side of it. Next up, we've got this CH2, which is a different environment because of what it's bonded to. We've got a CH2 and a CH3. Of course, they're non-equivalent to each other. They're different environments. So that's why we get a multiplet again of 6 CH3. And a CH2 is 5 hydrogen neighbors. So that's why it's a multiplet of 6. Oh, no, hang on. Which one am I doing? The third one? No, fourth one. Yeah, so it's this one. Get confused. And then lastly, we have got the CH3 environment, nice and easy, next to the CH2, and that causes a triplet. Okay, so going through the motions, as you do this, all this information here, this is you racking up marks towards these questions that you do, okay, by analyzing the spectrum, but this time we're analyzing the molecule, of course. But if you can do this, you can work in reverse, okay, you can work in reverse. And then lastly, we've got our benzene. The CH3 here has no hydrogen neighbors. One thing a lot of students kind of think is, oh, there's a hydrogen there, so it should be a doublet. There isn't, okay? In benzene, it's C6H6. If you've got anything substituted in on that benzene ring, like this CH3, there's no hydrogen on that carbon in the ring that it's bonded to, okay? It's literally only bonded to 3 things, all right? And of course, that 4th electron, we should know, is delocalized. So that's why it's a singlet. The 2 CHs, I'm just going to draw them like this. We have got none on the central carbon where the CH3 is bonded, as we've said, but we do have 2 hydrogens here, okay, as their next door neighbors. So that's why that's a doublet. Why is it not a triplet, guys? Good. They're equivalent to each other. So these 2 in red down here, they are in the same environment. So they only cause 1 set of splitting, and that's why that's a triplet. And of course, the same deal here for those 2. We're inverting it. We got these 2 hydrogens up here, which causes a doublet split, okay? But then, of course, we've got this other one here as well. So technically, we've got 1, 2 hydrogen neighbors. These 2 are counted as 1, remember, because they're equivalent. So we've got 2 hydrogens and then, as neighbors. So that means they have got a triplet. I thought only 1 hydrogen on the carbon in benzene. Yeah, that's what I'm saying, Sam. Yeah. There's only 1 hydrogen on each of these corners of the benzene ring. So wouldn't purple be doublet? No, because we've got, oops, excuse me. We've got 3 hydrogens. 1, 2, 3 as these are the neighbors of the purple ones. Okay. But because these 2 up here are equivalent to each other, they only cause 1 split. And then this down here causes a second split, okay? Or this, well, the second kind of neighbor hydrogen. So 2 neighboring hydrogens equals a triplet. You with me, Sam? So Sam's asking, why isn't it a doublet? Okay, good stuff. And then lastly, we have got this hydrogen down here. It's got 2 hydrogen neighbors, but they're equivalent to each other. So that's why it's only a doublet, not a triplet, because those 2 are equivalent to each other, okay? So that's really, really important that, that you understand that. It's a really important skill, kind of watching out for those, neighboring equivalent environments. They only have 1 impact on the splitting, okay? 1 impact on the splitting. So we're building up a picture now. We're building up, we know how many environments we've got, we've identified them, we know the relative peak heights, we know the splitting patterns for each one. Lastly, it's the chemical shift, okay? So let's put this in here. Last one, excuse me. Go back to black. There's a song in there somewhere. So chemical shift value, okay, in parts per million. You sometimes see it as a little sigma there like that. What dictates where it is, the peak on the x-axis, the chemical shift, in other words? What dictates that, ladies and gents? The data booklet does tell us that, yes, but what is it about the molecule that dictates it? Not how heavy, that would be mass spectrum. So you get a chemical shift value, not the polarity. Yeah, polarity does have an impact, but we're really not bothered about that. It's literally the type of environment. Okay, so the type of environment, i.e., where the hydrogens are relative to other things in the molecule. Okay. Question from Sam. Rich, if you had two same functional groups on different molecules and you're asked how do you identify using infrared, would you say look at fingerprint region? Yeah, fingerprint region is not something that any exam board focuses on. I know a lot of teachers talk about it. I just ignore it. It's like that over there, that's just not useful. But I think if you had two different molecules that had the same functional group on, there will be other stuff in the question to help you dissociate between one and the other. You need more than just IR. They would never ever do that to you in an exam from my experience. I've never come across a question where you need to get involved in the fingerprint region. Only in like old spec papers, right? It's just not a thing now. So if you've got two molecules, both have the same functional group, both same molecular formula and stuff like that, the only way you can get around this is by looking at fragmentation, maybe if that's in your spec for the mass spec, or indeed maybe looking at chemical tests, something else they might put in there. So it might be a secondary alcohol, a primary alcohol, or a tertiary alcohol, or indeed H-NMR. H-NMR would help you dissociate those things as well. Okay. Or C-NMR as well, Jawdul. Absolutely. Okay. So yeah, that's it. Compare data off internet or something. Yeah, I just haven't seen questions like that. And if you have come across questions like that, they'll be old spec ones and they're not doing you any favors. They're just making you a bit more concerned and a bit more confused. So my advice is just stick to the new spec questions, or indeed the questions that we've curated for you on the TT in a TT exam guide, or in the revision packs that I've given you as well, because I have used older spec questions in those, but I've vetted them so they're all relevant to you. Okay, there's nothing in there that you do or don't need to know. Yeah, I mean, lots of schools do, because we're still relatively early on in this specification in terms of the number of years, and we're lacking in papers, not least because the exam boards have kept the 2019s and October 2020s underneath their belts until after this exam series. So we are struggling in terms of how many past papers we've got, but at TT, we've got you covered, and you just need to know that the questions you're doing are relevant, and most teachers are very good at doing that. Some teachers not so much. Everybody's different, aren't they? And I've made faux pas in the past, like, oh, that shouldn't be in there. It doesn't work anymore. But Sam, do I use different exam boards for the end of topic question packs? No. So if you're EdXL, they're all old EdXL questions. If you're AQA, they're all old AQA questions. But like I say, I've vetted them all. They're all absolutely 100% relevant, because chemistry is still chemistry, right? But it's just little differences, like, there might be some Arrhenius, for example, wasn't in the old spec questions. So it wasn't in the old spec. So there's no old spec questions for it. The old spec was a different type of mass spectrometer. It was the deflection as opposed to the time of flight. So again, all those are different as well. So I've gone through them. I've curated them. Question in the YouTube chat, 2019 still locked? They are indeed. I'm sure they're out there, and they're 2020s. If you look hard enough, you will find them, but officially they're not publicly released, which means that we, as a business, we are a business at the end of the day. We can't be seen to be sharing things that aren't publicly shareable. So we're just playing by the rules. But like I said, some places don't, and some people don't. So there's always going to be somewhere in the darkest corners of the internet where you can find those sorts of things. Okay. Student room, absolutely. Yeah, it's hard to find Arrhenius questions because there's very few out there. Anyway, we're digressing, ladies and gentlemen. What I would like you to do is use your data sheet. So there's the EdXL, AQA, or OCR. I want you to put a range, okay? Don't put a value, put a range. So what I would say is, so for ethanol here, let's get this OH, for example, all right? So for that OH, I'm going to go to, just because I can, the AQA, and I'm going to find my OH. So this is an OH alcohol. So what I would say is, that's an OH acid, that one there. So it's not that one. Where is it? Oh, there it is, right at the top. 0.5 to 5.0. Thank you very much. I was looking from the bottom up for some stupid reason. So what I do in here is I put 0.5 to 5, which doesn't help, does it really? It really doesn't help, all right? Because that is a massive, you can put that anywhere you like, and it really depends on, what else it's bonded to, wherever in the molecule it is, and so on and so forth. But you know what? Just put down the range, okay? Just put down the range. So that's what I want you guys to do. Try and put a range or a chemical shift for each of those things. I'm going to do it for AQA, all right? I know not all of you are AQA, and your answers might be slightly different to what I'm putting here. This is the danger. So, you just have to trust yourself that you can do this. So again, I'm going to give you 5 minutes, and that 5 minutes has started. And I'm going to pause my sharing so not to give away the answers. Shania is saying that chemistry teacher said if you can't find an exact one in the data sheet for something, look for something that that is most similar. Okay, so RCH2, yeah. So RCH2 is basic, or R2CH2, isn't it? Because when you got a CH2, you got R groups either side of it normally. Okay. Yeah, this bit of NMR is the trickiest bit. You're right there, Emily. Emily's saying they find it really hard, this bit. And time is up. Okay, so like I was saying, I am working on the AQA data sheet. Okay, so if your answers are different to mine, excuse me, then that's probably because you're using OCR and Excel data sheets. The data you'd think would be different. You think it'd be universal. You think they'd be unanimous in their approach to this, but they're not. So word to the wise, before we look at these, if you are doing a Q-rated paper in the exam guide, so if you're AQA and you're doing an OCR question or an EdXL question or any other combination, then you need to use their data sheet. All right, because that's what's going to be referred to in the mark scheme. So whatever exam board you're using, okay, in order to practice these things, then just make sure you're using their data sheet. All right, really, really important. So resuming share, what I've got here for AQA is basically this one's a CH3 and RCH3, which is 0.7 to 1.2. This is a CH2, which is 3.1 to 3.9. But I've used this one because it's next to the O. Okay, so that's what we're looking at in the data sheet there. So because that CH2 is next to an O, that's why I've used 3.1 to 3.9 and OH 0.5 to 5. And I think, was it before Sam said something's about as useful as an OH chemical shift in the data sheet. Yeah, exactly. It's just like, wait, what's down there somewhere, isn't it? Okay. So just quickly, I mean, I know it's going to be different for lots of you. 0.7 to 1.2 for the CH3. We've got a CH2 there, nothing to write home about. 10 to 12 for the OH acid right at the bottom there. 0.7 to 1.2 twice because we got the H. I didn't know what to use here because there wasn't anything like, you know, the hydrogen next to a COOH or anything like that. So I just plugged for a regular alkyl group. CH3 and an NH is very precise. It's between 1 and 4.5. For this one, again, lots of stuff, 0.7 to 1.2, 1.2 to 1.4 for CH3, CH2. But this one here, the H that's bonded to a C that's also bonded to a chlorine is 3.1 to 4.2. 1.4 to 1.6, isn't it, that one, Rich? R3CH. For this one, possibly. I mean, is that an R group? This isn't an R group, though. Come on, Rich. This isn't an R group, is it? So maybe not. They've got to give you some leeway with this. This is why it's the most difficult part. Okay. Next up, lots going on here. Again, lots of 0.7 to 1.2, 1.2 to 1.4, because there's just alkyl stuff going on. Again, 3.1 to 4.2, because we've got a hydrogen bonded to a carbon. It's also bonded to a chlorine. And then I'd put this 0.7 to 1.2 on the end again here. So really busy low end of the spectrum here, okay? And then lastly, we've got 0.7 to 1.2 for our CH3 here, but actually in the AQA, and I didn't realize this until just now, in the AQA data sheet, there actually isn't one that refers to benzene specifically. Okay, none of those actually refer to benzene. So I don't know. I mean, in EdXL, where you've got an arene ring, okay, hydrogen, it's between 7 and 8. Okay, and it's the same actually for or 6.5 to 8 is a hydrogen on a benzene ring. So that's what I'm going to go for there. I'm going to put that 6.5 to 8, 6.5 to 8, and 6.5 to 8. Now, of course, the reason they don't ask you to draw these, okay, in an exam question most of the time, exactly what would AQA do? I think if AQA were asking you about a benzene ring and H-NMR, they would definitely put it in the data sheet for that exam, okay? They'd have to put it in the data sheet for that exam, all right? So they can change the data sheet year on year. That tends not to change much or at all, to be honest. But yeah, if it's not in a data sheet, they can't ask you it, okay? They can't ask you it. Jodel, my teacher says, if you're not sure, just leave it and do everything else the question asks. I would absolutely 100% agree with that. 100% agree with that, okay? So essentially, those are the 4 things that you need to know. Those are the things that are going to get you your marks. But of course, what you're doing in an exam situation most of the time is actually looking at the spectrum and making your inferences from that spectrum, as well as other information they've got you, they've given you in the question. So just by understanding these things, okay, and like I said, reverse engineering this process, looking at a molecule and just saying, right, this is what it's going to look like. So I would say practice this. What I've given you is one at the end where you can just print out as many as you like and just give yourself random molecules to do to practice. Okay, so I've put that one on the end there. Got a little note to self. You've got your H-NMR, sorry, your spectrum at the bottom. Okay, so the only thing, this is kind of not related to anything. Well, it is related to something, but what I would say is another thing to look out for is this. This is pretty common, an ethyl group. Okay, an ethyl group. Now, because they're both alkyl groups, you're going to get a CH2 next to a CH3. So that CH2 is going to be a quartet like that, and the CH3 is going to be a triplet like that. Okay, so you get a quartet and you get a triplet. This is 2 high and this is 3 high in terms of integration values. Remember that little combo: a quartet at 2, a triplet at 3. That is an ethyl group, and you see them quite often. So it's just another little kind of quirk, a little tip for you that I've kind of come across over the years. So when you see that combination, quartet, triplet, you got a CH2, CH3 going on, okay? So just be wary of that one, because this is most likely like maybe bonded to an O for something else, okay? Hearing the word integration in chemistry gives you anxiety. Well, don't let it give you anxiety, mate. Integration values. You know, those integration values, it's just a ratio. It's finding the simplest ratio in terms of whole numbers. That's all you need to do there, okay? And like I said, once you found that simplest whole number ratio, just like empirical formula or anything like that, it's all it is. You've got the number of hydrogens in each environment, the actual number of hydrogens, okay? So I'm going to love and leave you now, guys, because we've done an hour and a half. I'm going to leave you to draw, okay, in your own time, if you want to, these different spectra, so you get an idea of what they look like. I've actually changed them slightly because this one's going to 6, because obviously we've got a integration value of 6, or you can, these are 4. The other thing I will get you to do, those of you in TT members, I would encourage you to go and watch my H-NMR videos and do the quizzes there, okay? Do the quizzes there. The worksheets are really good. Really, really pleased. Yeah, I'm so pleased you found them really useful. Try the quizzes, okay? If you're on the YouTube live, there's a link to those 2 quizzes that I've got for H-NMR in the course. So you can have a go at those. It will give you a score at the end of it. You can view the correct answers. So this just takes practice, okay? And if you're really worried about these coming up in your exam, literally go to your exam board in the exam guide, search for past paper questions by topic, search for H-NMR, and do every single question you can get your hands on, okay? Because you know what? With these assessments you guys are having, they're using older material, right? So, you know, they're already released material. So the best thing you guys could be doing now with your revision, generally speaking, is just smashing through as many past papers as you can. Okay, that is the thing. Is it going to be a study session for chemistry this evening? There is not, I'm afraid, because we're doing, we're tripling up on our lives the last couple of weeks. So there won't be a live class tonight, but next week we are back to normal and chemistry will be on a Wednesday at 5:30 for a couple of hours. Okay. As I say, I'm coming back tomorrow. In fact, I'm going to stop sharing so I can speak to you. I'm coming back tomorrow to do some enthalpy stuff with you, okay? Now, have you heard the phrase like, give a man a fish, he'll eat for a day. Teach a man how to fish, then he can feed himself for a lifetime, right? So it's both, Shania. So tomorrow we're looking at enthalpy from mean bond energies to calorimetry to Hess's law, to Born-Haber cycles, to enthalpy of solution, lattice enthalpy. We're going right the way through, and we're going to have a big whistle-stop tour all the way through. Okay, so the first half is going to be suitable for everybody because it's AS stuff, and the second half obviously is year 13 focus stuff only. Okay, so I'm just going to give you a bunch of questions, and I'm going to give you my tips for my best tips for actually smashing those questions. Okay, so it's not about, oh, just sit and watch me do a question. That's like the equivalent of me giving you a fish. Like, here's the answer to this question. Well done, Rich. You're a chemistry teacher and you're very good at doing questions. What I'm going to do is give you some hints and tips and methods, okay, methodologies to actually help you through these questions, because we all know with these calculations and stuff like that, small errors can lose you lots and lots of marks. Okay, there's a lot of FFS that goes on in these enthalpy questions, and we want to do the job. If you say it like that, it sounds wrong. And I'm not going to repeat what you said in the chat there, because you're just making double entendres with what I'm trying to say. Yes. Okay. We'll leave that there. That is funny though. Is that thermodynamics? Yes, it is, Subnam. Okay. So it is thermodynamics, and we'll be going right from the very start right to the end. So I'm just going to be throwing questions at you and giving you my hints and tips as to how to attack them. Okay, so we won't necessarily even be doing the questions. We'll be just talking about what, we'll be analyzing the questions and talking about how we can get those through. So it will be a slightly shorter one tomorrow. I do apologize for that. It's going to be about an hour, just over an hour, okay, rather than the usual hour and a half to 2. That's because I've got a previous appointment that I have to attend, sadly. But 11 till 12 tomorrow, we're going to be looking at exam technique on, well, you can apply these tips and things I'm going to give you tomorrow to other questions as well, but we're using enthalpy as a platform to in order to get those out to you. Okay, so thank you very much for coming again today, guys. Really appreciate it. Hopefully you found this useful. Now, like I said, I know this was a little bit kind of like simple, and we weren't doing exam questions today, but like I said, as well as I do, that 9 times out of 10 with these, it's lack of understanding of the principles and how we get these things sorted. So, by doing what we've done today, we're just reaffirming what the rules are, and you can apply those rules. And I'm sure there's something that everybody's learned today. Okay. So thanks very much, guys. I will love you and leave you, and I will see you tomorrow at 11. Rich will see you later tonight at 5:30. And as I say, I'm pretty sure Ronnie's doing a regular live class tomorrow at 5:30. Okay. So I will see you tomorrow.